Algebra 2, Chapter 13.3, exercises 12 through 19. Find a function represented by each graph and state the domain and range using set notation. So what we're going to do here is we're given 2 points that are the transformations of the reference points starting out at 0, 1. And so we're going to find what it takes to transform to this point here. We're going to start with the parent function, which is f of x equals a times base to the power of x minus 8 plus k. And we're going to start with this point here, and then work backwards. And I'm going to work out the odd number problems in these sets. I'm going to go straight to 13 and go from there. And so you start out with the point 0, 1, which is our original y-intercept, and we're transforming it over to here. So this negative 4, 1 is the transformation of 0, 1. So the original function, that's going to be f of x equals a times b to the power of x minus h plus k. And really, based on what we see here, your starting value, your y-intercept is k, so k is going to be equal to your y-intercept. It turns out to be that here, but it's your horizontal asymptote, so k is equal to 3. And this reference point being negative 4, it's going to be h is going to have to be negative 4, because if we have h minus negative 4, that's how we get x plus 4. So what we're going to have is f of x equals a times b to the power of x plus 4 plus 3. And we're going to go ahead and put in for, we don't know what a is. We're not going to know that initially. So we're going to have to solve for that, and we don't really know what b is. But we're going to be using this point here, negative 4, 1. So we replace where we can 1, which is replacing f of x, equals a, which we don't yet know, times b, which we don't yet know either, times x. X is going to be negative 4. So we have negative 4 plus 4, which is going to be 0, plus 3. And that's going to equal 1 equals a times b to the 0 power plus 3. And we know that b to the 0 power is 1. So 1 equals a plus 3. And subtracting 3, a is going to be equal to negative 2. Now we're going to use our second reference point, which is a transformation of from negative 1, comma, whatever ends up being here. So let's just work out the second point right here. So we're going to have negative 3 equals a. Well, a we already know is negative 2. Negative 2 times b to the power of negative 5. That's going to be negative 5 plus 4 plus 3. Now, So we just go about solving, and if we subtract 3 from both sides of this equation, we get 0 is equal to -2 times, let's see, 0, -6. -6 equals -2 times b to the power of -5 plus 4. That's going to be -1. And so what we're going to get is, dividing by -2, we get 3 is equal to b to the -1 power, which is going to be 1, over b. And just, if we just flip the fractions upside down, b is going to be equal to 1/3. So our function here is going to be f of x equals -2 times 1/3 to the power of x plus 4 plus 3. And then you can try and calculate it to see if you get the same thing. So here is our calculator. So we're going to put in -2 times 1/3 to the power of x plus 4, and come outside here, plus 3. And then the graph, what does that look like? Looks like this right here. If you go to table view, you should see the points. Okay, we have -4, 1, check. -5, -3, so they both check. So this would be our correct answer. Let's go back and try to do the same thing with number 12. The same process, just follow along and do the best on that. Okay. Next on the problem, 15 paleontology, carbon-14 is a radioactive isotope of carbon was used to date fossils. This is one of the real-world uses that I talked about earlier in introducing the topic. There are about 1.5 atoms of carbon-14 per trillion atoms of carbon in the atmosphere. And gradually this carbon-14 decays to become, turns into carbon-14, it just decays to become nitrogen, I think. Anyway, it goes away over time. So anyway, what we have for exponential function, this is a is going to be equal to a sub 0 starting amount times 1 plus r to the power of t. That's what it would really look like. Now here we're given a rate of decay of 11.4%. So r is going to be equal to 11.4%. Well, it's going to be negative 11.4%. And in our formula here, I need to go ahead and put in, make it a decimalized form. So it's going to be negative 0.114. And so our equation is going to be A equals A sub 0, and we're given a starting amount, okay, which is 1.5 parts per trillion, and 1 minus 0.114 to the power of t. And t is going to be as a function of time in millennia, which means thousands of years. And so it's going to be A is equal to 1.5, and then 0.886 to the power of t. 86. Okay, and it's going to be an equation, and to determine the amount of time, if we set this other side equal to find the amount of time it takes to get 0.2 parts per trillion, we put 0.2 equals 1.5 times 0.886 to the power of t, and t is going to be in millennium. So we can go to the calculator and figure that out. So the equation we put in here is 1.5 times 0.886 to the power of x. I'll put this there. And if we graph this function, this is what it looks like. We're going to find the number of millennia. To do that, we're going to find how long it takes to get to 0.2 parts per trillion graph. And you're looking for an intersection point here. I'm not quite seeing the intersection point. I'm going to change the window a little bit. From 0 to 50,000 years is the maximum date for problem 14. So I'm going to do 15. And y minimum, I'll keep it, I'll make it negative 1. And y maximum, I'll make it 3. And it starts at 2.5 and then 1.5. Looks like this. We see the intersection point, intersection point second, trace, 5, enter, enter, enter. So we get 16.65, looks like 16.645. So 16.6. Actually, you can write, if it's in thousands of years, it would be 16,647 years. Um, 647. 16,647 years. Now, I happen to know that this is the column 14 half-life formula is this, is the amount is equal to A sub 0 times 1/2 to the power of t divided by 5,730 years. So that would be a regular looking half-life formula. I'm going to go back to the calculator just to show you what it looks like. We'll do that as 0.2 and put 1.5 times 5,730 0.5, which is half-life to the power of, we're going to have x over the half-life of carbon-14, which is 5,730 years. And in this case, we're in years. If you graph, you can't see very much. They just look like horizontal lines, which they're not. If you go to window and go from 0 to 50,000 every 10,000 years, you should be able to see this fine. And do the same thing here. Second, trace, 5, enter, enter, enter. You get roughly the same thing, 16,656 years. Yeah, very close. So just to show you what that is. So, very close. Anyway, let's go to problem 17. This is analyze relationships. Compare these two graphs, f of x and g of x. F of x equals 1/2 the power of x, and g of x equals x to 1/2 power. So we have f of x equals 1/2, which is our base, to the power of x, and g of x equals x to 1/2 power, which is equal to the square root of x. So basically, the square root of x, what that function looks like is this. I'll just put the calculator. I'll go to 6. Erase everything. We got square root of x. Which is this one right here. And we have x to, we have 1/2 to the power of x. It would look like this. So we're comparing the different domains, range, and behaviors of these. So we're going to have this one here is going to be square root of x, and this one right here is going to be 1/2 to the power of x. G of x. So that's what we're looking at. Domain. So which the properties are the same. Well, I don't know if any of the properties are the same. So for domain f of x for domain is equal to all real numbers, right? And for g of x, domain is going to be greater than or equal to 0, less than infinity. Okay, range f of x, range is going to be greater than 0, less than infinity. For g of x, your range is going to be not greater than 0, but greater than or equal to 0, because you can actually start at 0 and go up toward infinity. And behavior as x increases, as x approaches infinity, f of x approaches, so we're going toward 0. As x approaches infinity, g of x approaches, that's the square root function here, approaches infinity. So they are different. We've had different every insofar. And for this f of x here, for any behavior as x decreases, as x approaches negative infinity, f of x approaches infinity. As x approaches negative infinity, g of x doesn't even exist. You don't go past the y-axis. G of x does not exist. So, which of the following properties are the same? Well, the answer is none. We'll just explain by working out all these characteristics. Okay, last, multiple representations. Exponential decay functions are written as transformation function f of x equals b to the x, where b is between 0 and 1. However, it is also possible to use negative exponents as the basis of an exponential decay function. Use the properties of exponents to show why the function f of x equals 2 to the power of x is an exponential decay function. So I'm going to write this down. F of x equals 2 to the power of negative x. And what we can do is we can rewrite this as 2 to the power of negative x. And we can distribute this negative sign. So we can rewrite this as 2 to the negative 1 power to the power of x. And we can rewrite 2 to the negative 1 power as 1 over 2 to the power of x. So we have f of x equals 1/2 to the power of x. And so since b is greater than 0 but less than 1, we have an exponential decay function. Really, that is it. So that concludes this video lesson. Good luck. Thanks for doing it.